Greetings, fellow scholars. Welcome back to our channel. Today, we're delving into the intricate world of radar technology and uncovering the mysteries behind the radar equation. This fundamental tool sits at the very heart of radar technology, helping us understand how radar systems detect and measure targets in their environment. But what exactly is the radar equation? It's a mathematical expression that relates the transmitted power, antenna characteristics, target properties, and environmental factors to the received signal strength. That's right, it's the key to unlocking how effectively a radar system can detect and track objects in its vicinity. So, let's embark on this journey of discovery together as we unravel the complexities of the radar equation. At its core, the radar equation is a mathematical expression that relates the transmitted power, antenna characteristics, target properties, and environmental factors to the received signal strength. Let's break down the components of the radar equation, shall we? This equation is a fascinating blend of different elements, each with its own unique role in the grand scheme of radar technology. First up, we have the transmitted power. Think of this as the initial energy boost that sets the radar signal on its journey. The transmitted power represents the strength of the radar signal that the transmitter emits. It's like the initial push you give a swing. The stronger the push, the higher the swing goes. Similarly, the higher the transmitted power, the further the radar signal can reach. Next in line is the antenna gain. Now, this isn't about gaining weight or height. In the world of radar technology, gain refers to the directionality and focusing of the radar beam. The antenna gain determines how the radar signal is directed and focused, much like how a torchlight focuses light in a specific direction. The higher the antenna gain, the more focused the radar beam, allowing it to target specific objects with greater precision. Lastly, we have the target's radar cross-section. This is a measure of how well the target can reflect radar signals back to the receiver. Imagine throwing a ball at a wall. The harder the wall, the better it reflects the ball back to you. Similarly, the larger the target's radar cross-section, the stronger the reflected radar signal and the easier it is for the radar system to detect and track the target. So to sum it all up, the radar equation is a delicate dance between the transmitted power, antenna gain, and the target's radar cross-section. Each component plays a vital part in determining how effectively a radar system can detect and track objects in its vicinity. Next, we have the target's radar cross-section, which quantifies its ability to reflect radar signals back to the receiver. Now, you might be wondering, what are the real-world applications of the radar equation? Well, the applications are as vast and varied as the waves that radar systems emit. Radar technology, underpinned by the radar equation, plays a pivotal role across a wide spectrum of industries and fields. One of the most common applications is in weather monitoring. Meteorologists harness the power of radar systems to track storms and predict severe weather events. By analyzing the radar echoes, they can determine the location, movement, and intensity of storms. This valuable information aids in disaster preparedness and ensures public safety. Next, let's take a look at air traffic control. Air traffic controllers use radar systems to keep a watchful eye on the skies. The radar data provides real-time information about aircraft positions, speeds, and altitudes. This is crucial for managing air traffic, preventing collisions, and ensuring the safe and efficient operation of our airways. But the reach of radar technology doesn't stop there. It extends into the realm of military surveillance and space exploration as well. Military forces around the globe rely on radar systems for detection and tracking of potential threats, enhancing their situational awareness and defensive capabilities. And in space exploration, radar technology helps scientists map the surfaces of planets, track asteroids, and study distant celestial bodies. So, whether it's forecasting a hurricane, guiding a plane to safe landing, detecting a submarine underwater, or mapping the surface of Mars, the radar equation is hard at work, making it all possible. It's the invisible hand guiding the pulses of radio waves that radar systems emit, dictating how they interact with objects and return to the receiver. Similarly, air traffic controllers rely on radar data to monitor aircraft movements and ensure safe and efficient airspace management. So, as you can see, The radar equation is not just a mathematical formula, it's a powerful tool that drives the operation of radar systems and shapes our understanding of the world and beyond. However, it's important to acknowledge that the radar equation is not without its challenges and limitations. Just like any other scientific process, it's influenced by a range of factors that can sometimes make its application a bit tricky. One major challenge is atmospheric conditions. Rain, dust, and other particles in the air can scatter radar waves, diminishing the signal strength and potentially leading to inaccurate measurements. Size and shape of the target also play a significant role. A small object or one with a complex shape can be difficult to detect accurately, as it might not reflect the radar waves effectively. Lastly, interference from external sources, such as other radar systems or electronic devices, can distort the radar signal, making it harder to interpret the data. Factors such as atmospheric conditions, target size and shape, and interference from external sources can impact the accuracy and reliability of radar measurements. But fear not, my diligent scholars, for every challenge presents an opportunity for innovation and advancement. As we've seen today, the radar equation, while complex, serves as a vital tool in understanding and leveraging radar technology. We've delved into its components, explored its various applications, and acknowledged its limitations. Yet it's these very challenges that spur innovation, driving us to refine and enhance our radar systems. In our journey, we've uncovered the essence of the radar equation, seeing how it links transmitted power, antenna characteristics, target properties, and environmental factors to the received signal strength. We've seen its wide-ranging applications from weather forecasting and air traffic control to military surveillance and space exploration. And there you have it, my esteemed learners, an enlightening journey through the principles of the radar equation and its profound impact on remote sensing and radar engineering. Let's continue pushing the boundaries of knowledge, forever unlocking the universe's secrets.